The slope of the hill was 9½ degrees, or a drop of 1 foot in 6. We found that after attaining a speed of about 25 to 30 miles with reference to the wind, or 10 to 15 miles over the ground, the machine not only glided parallel to the slope of the hill, but greatly increased its speed, thus indicating its ability to glide on a somewhat less angle than 9½ degrees, when we should feel it safe to rise higher from the surface. The control of the machine proved even better than we had dared to expect, responding quickly to the slightest motion of the rudder. With these glides our experiments for the year 1900 closed. Although the hours and hours of practice we had hoped to obtain finally dwindled down to about 2 minutes, we were very much pleased with the general results of the trip, for, setting out as we did with almost revolutionary theories on many points, and an entirely untried form of machine, we considered it quite a point to be able to return without having our pet theories completely knocked on the head by the hard logic of experience, and our own brains dashed out in the bargain. Everything seemed to us to confirm the correctness of our original opinions. 1. That practice is the key to the secret of flying. 2. That it is practicable to assume the horizontal position. 3. That a smaller surface set at a negative angle in front of the main bearing surfaces or wings will largely counteract the effect of the fore and aft travel of the center of pressure. 4. That steering up and down can be attained with a rudder without moving the position of the operator's body. 5. That twisting the wings so as to present their ends to the wind at different angles is a more prompt and efficient way of maintaining lateral equilibrium than that employed in shifting the body of the operator of the machine. When the time came to design our new machine for 1901, we decided to make it exactly like the previous machine in theory and method of operation. But as the former machine was not able to support the weight of the operator when flown as a kite, except in very high winds and at very large angles of incidence, we decided to increase its lifting power. Accordingly, the curvature of the surfaces was increased to 1 in 12 to conform to the shape on which Lilienthal's table was based, and to be on the safe side, we decided also to increase the area of the machine from 165 square feet to 308 square feet, although so large a machine had never before been deemed controllable. The Lilienthal machine had an area of 151 square feet, that of Pilcher 165 square feet, and the Chanute double-decker 134 square feet. As our system of control consisted in a manipulation of the surfaces themselves instead of shifting the operator's body, we hoped that the new machine would be controllable, notwithstanding its great size. According to calculations, it would obtain support in a wind of 17 miles per hour, with an angle of incidence of only 3 degrees. Our experience of the previous year having shown the necessity of a suitable building for housing the machine, we erected a cheap frame building, 16 feet wide, 25 feet long, and 7 feet high at the eaves. As our machine was 22 feet wide, 14 feet long, including the rudder, and about 6 feet high, it was not necessary to take the machine apart in any way in order to house it. Both ends of the building, except the gable parts, were made into doors which hinged above, so that when opened they formed an awning at each end and left an entrance the full width of the building. We went into camp about the middle of July, and were soon joined by Mr. E. C. Huffaker of Tennessee, an experienced aeronautical investigator in the employ of Mr. Chanute, by whom his services were kindly loaned, and by Dr. A. G. Spratt of Pennsylvania, a young man who has made some valuable investigations of the properties of variously curved surfaces and the travel of the center of pressure thereon. Early in August, Mr. Chanute came down from Chicago to witness our experiments and spent a week in camp with us. These gentlemen, with my brother and myself, formed our camping party, But in addition, we had in many of our experiments the valuable assistance of Mr. W. J. Tate and Mr. Dan Tate of Kitty Hawk. It had been our intention when building the machine to do most of the experimenting in the following manner. When the wind blew 17 miles an hour or more, we would attach a rope to the machine and let it rise as a kite with the operator upon it. When it should reach a proper height, the operator would cast off the rope and glide down to the ground just as from the top of a hill. In this way we would be saved the trouble of carrying the machine uphill after each glide, and could make at least 10 glides in the time required for one in the other way. But when we came to try it, we found that a wind of 17 miles, as measured by Richard's anemometer, instead of sustaining the machine with its operator, a total weight of 240 pounds, at an angle of incidence of 3 degrees, in reality would not sustain the machine alone, 100 pounds, at this angle. Its lifting capacity seemed scarcely 1/3 of the calculated amount. In order to make sure that this was not due to the porosity of the cloth, we constructed 2 small experimental surfaces of equal size, one of which was airproofed and the other left in its natural state, but we could detect no difference in their lifting powers. For a time we were led to suspect that the lift of curved surfaces little exceeded that of planes of the same size, but further investigation and experiment led to the opinion that 1. The anemometer used by us over-recorded the true velocity of the wind by nearly 15%, 2. That the well-known Smeaton coefficient of 0.005 v² for the wind pressure at 90 degrees is probably too great by at least 20%. 3. That Lilienthal's estimate that the pressure on a curved surface having an angle of incidence of 3 degrees equals 0.545 of the pressure at 90 degrees is too large, being nearly 50% greater than very recent experiments of our own with a special pressure testing machine indicate. 4. That the superposition of the surfaces somewhat reduced the lift per square foot as compared with a single surface of equal area. In gliding experiments, however, the amount of lift is of less relative importance than the ratio of lift to drift, as this alone decides the angle of gliding descent. In a plane, the pressure is always perpendicular to the surface, and the ratio of lift to drift is therefore the same as that of the cosine to the sine of the angle of incidence. But in curved surfaces a very remarkable situation is found. The pressure, instead of being uniformly normal to the chord of the arc, is usually inclined considerably in front of the perpendicular. The result is that the lift is greater and the drift less than if the pressure were normal. Lilienthal was the first to discover this, exceedingly though our measurements differ considerably from those of Lilienthal. While important fact, which is fully set forth in his book, Bird Flight, the Basis of the Flying Art, but owing to some errors in the methods he used in making measurements, question was raised by other investigators not only as to the accuracy of his figures, but even as to the existence of any tangential force at all. Our experiments confirm the existence of this force. At Kitty Hawk we spent much time in measuring the horizontal pressure on our unloaded machine at various angles of incidence. We found that at 13 degrees the horizontal pressure was about 23 pounds. This included not only the drift proper, or horizontal component of the pressure on the side of the surface, but also the head resistance of the framing as well. The weight of the machine at the time of this test was about 108 pounds. Now, if the pressure had been normal to the chord of the surface, the drift proper would have been to the lift, 108 pounds, as the sine of 13 degrees is to the cosine of 13 degrees, or 0.22 times 108 divided by 0.97 equals 24 plus pounds, but this slightly exceeds the total pull of 23 pounds on our scales. Therefore it is evident that the average pressure on the surface, instead of being normal to the chord, was so far inclined toward the front that all the head resistance of framing and wires used in the construction was more than overcome. In a wind of 14 miles per hour, resistance is by no means a negligible factor, so that tangential is evidently a force of considerable value. In a higher wind, which sustained the machine at an angle of 10 degrees, the pull on the scales was 18 pounds. With the pressure normal to the chord, the drift proper would have been 0.17 times 98 divided by 0.98 equals 17 pounds, so that, although the higher wind velocity must have caused an increase in the head resistance, the tangential force still came within 1 pound of overcoming it.